There's such a, there we go. Okay, whoops, wrong way. For those of you that have joined us today, welcome. Great, I see my internet is unstable. Maddie, let me know if I start warbling. So one of the things, Maddie, is I can no longer see the panelist box.
Okay.
There we go. I get this wicked delay. Now I can. So for those of you that are joining us, welcome. We're going to be starting in a few minutes at 3 o'clock at our scheduled time. We'd love for you all to introduce yourselves in our chat box today. Just make sure you click on all panelists and attendees. Let us know your name and where you're from. So, hi everyone. I see we have Adrian from Rhode Island. That's awesome. Oh, Fast and Furious coming in. Oh, Landon Quincy. I know you guys from Bakersfield. It's funny. There's some, I do know a lot of people that come on in. So if you're just joining us today, find the chat box. You might have to hover your mouse down towards the bottom of your screen and you'll see a menu. Chat box will be one of your options. Just make sure you choose all panelists and attendees before you start typing. Let us know where you're from, who you are. We're really excited to have you join us today. This is going to be a out of this world experience, right, Maddie? Can I do my space puns?
You can do as many space puns as you want.
Thanks.
My fiance is in the next room though, and she's heard all of them way too many times.
Ah. Hi, Cannon and Boone. I haven't seen you guys in a while. And we've got Moortown. We've got Pittsford, Vermont, and Shelburne, Vermont.
Hey, Shelburne.
Oh, that's right. That's where you're from, right, Maddie?
Yeah.
Nice. So for those of you joining us, hover your mouse towards the bottom of your screen. You'll find a menu bar. Click on the chat box. Before you start typing, make sure you choose all panelists and attendees. And then just tell us who you are and where you are from. We love to know where everyone is coming from today. It's so exciting to have these large gatherings from Vermonters all over the state. And we also, I know we have people coming from other states today as well. We got another Shelburne, Vermont. Nice. We're gonna keep allowing people to say hello. Give it a couple more minutes. I see we almost have close to 30 people on, but we're expecting about twice as many. So we'll give people a chance to log in, get connected, find the chat box, and introduce yourselves. So it's nice to see we have Fairfax and Burlington. We have someone from Maine. I'm always excited to see that because that's where I grew up. I'm a Mainer. And I love when we see Rhode Islanders because that's where I went to college. So I love when we get people from all over. We got Brandon, Vermont, nice, and Charlotte, Vermont, Jericho, fantastic. I see we're right at 3 o'clock, but Maddie, if you're okay, we'll give it another minute or so to let everybody come on into the webinar. It's great that you all have joined us today. We got another Shelburne, Vermont that just joined us. We're excited to have so many people with us for our quarantine virtual science cafe. Essex Junction is here with us today. Morrisville, awesome. That is right where I hail from. I'm sitting in Hyde Park, Vermont today. Sunderland. Sunderland's down south, right? I think. Shelburne and Morrisville. Awesome. We're up to 40, so we'll give it another minute and then we'll get going. Yes, it is. Thank you. I'm slowly learning after 20-something years my Vermont geography. We got East Calais. Nice.
Yeah, I've also been here for 20-something years, and I don't know where East Calais is. Sorry, man.
That's up near me. It's what is it technically? I think it's Orleans or Caledonia County. Oh, Andy.
I know. Dude,
you know
how's
Andy?
It going?
I know Andy.
That's crazy.
Yes, I see that Otis is on. So Andy, you're lurking in the background. That's fantastic. All right, we got about 40 something on. People are still, thank you. Why don't the panelists introduce themselves? We will be once we get started. We have the ability to speak, so we're not gonna do it through the chat, but we will introduce ourselves in about 30 seconds. All right, I'm gonna close out the chat for me so I can see my site. So we're gonna get started. We wanna welcome everybody today to our second quarantine virtual science cafe. I'm Lauren Traster. I am the 4-H Teen and Leadership Program Coordinator for UVM Extension. And many of you know that we have been doing in-person science cafes for a couple of years now. And because of our social distancing, we moved everything online, and it's really excited to have so many new folks join us for these cafes. Slides, there we go. I just want to go over some of our protocols for having these in our Zoom platform. So all of you are muted today, and that's just because there's so many of you. It's really hard to have people coming in and out of speaking roles. So everyone is muted, and we're gonna steer you into the chat box and the Q&A box. So if you hover your mouse down at the bottom of your screen, you'll see you have those two different options, and we're gonna use them very differently. The chat box is to give comments about if our presenter asks you to think about something and share an idea, you would write that in the chat box. The Q&A box is if you have a question for our presenter. And if you go into the Q&A box and somebody already asked the question you were thinking of, we've enabled this option called upvote, and you'll see there's a thumbs up. And you can just click on that thumbs up if that was your question. That tells us more than one person had that same question. So the chat box and the Q&A box are very different. And we're gonna ask today, especially in the chat box, to be courteous and respectful. What this means is try not to create any distractions, especially in the chat box. At our cafe last week, a lot of people were talking to one another, but it really was off topic, and it ended up being distracting for a lot of people. So if you have a friend that's on today, you might want to privately chat them. But in all honesty, you should just stay focused to what our presenter and what's being talked about today. So try to just, show respect in that manner, to not go overboard in the chat box today. We'd love that you stay engaged and participate fully, because I know our presenter, Maddie, has some really wonderful things to share with you today. So at this point, I want to introduce our presenter. Madeline Pomicter is a propulsion engineer. She is a native Vermonter who grew up dreaming of becoming a rocket scientist. She graduated from the University of Vermont in 2018 with a Bachelor of Science degree in neuroscience and mechanical engineering. She was introduced to SmallSat and CubeSat technologies during her time as a Mission Design Intern at NASA Langley, where she helped plan a mission to send a small satellite to Mars orbit. After graduation, she joined Benchmark Space Systems as a propulsion engineer, designing propulsion systems for small satellites. So if we can all just welcome Maddie today, I'm gonna stop sharing my screen, turn it over to Maddie, and really excited to learn about SmallSats.
Sweet. All right, let me pull up what I got for you here. All right. So, as Lauren just mentioned, I'm going to talk to you guys about propulsion engineering for small satellites today. But to start off with, I won't be too long with this because we kind of just went over it, but a little history about me and how I got to where I am right now. So I started out in Shelburne, Vermont, as some of you in the chat might have caught. I dropped out of school when I was in middle school and homeschooled for a couple of years, then found my way over to University of Vermont, where I majored in mechanical engineering and neuroscience. My goal with that was I wanted to do brain-machine interface engineering, but on my way through school, I took a little detour through NASA, got an internship down at NASA Langley, kind of coincidentally, where I was working on designing a small satellite that was supposed to go on a mission to Mars Phobos orbit. In case anyone's interested, it's not going to happen anymore. Then I went back to University of Vermont, graduated, and realized that the field I wanted to go into was really not ready for people with just a bachelor's in mechanical engineering or a little bit of neuroscience background. That if I really wanted to go into brain machine interfacing, I would probably have to go get like a PhD in computer science, which was not super interested in. So I did the logical thing and bought a one-way ticket out of the States, wandered around for a couple of months, and then eventually ran out of money and had to, come back, and found myself in Burlington again, kind of lost, not knowing what I wanted to do. And then sort of out of nowhere, this job listing popped up for a place called Benchmark Space Systems. Look, I had gotten at NASA. So I applied, and within a couple of weeks, I was working there and suddenly in the fields of rocket science, but really small. So whenever you're, in school, you're probably going to have some ideas, but it's kind of always a winding route to how you end up where you end up in your career. So I work on small satellites now. Small satellites are satellites that are under about 500 kilograms. There's a pretty wide range of satellites that we launch at the moment. So there are traditional satellites. Those are in your 500 plus kilogram range. I think of those as being like the size of a vehicle. So anything from a little car all the way up through a school bus. Then there are small satellites, which on the large end, and what people generally refer to when they say small satellite, is something 100 to 500 kilograms. That means it's the size of a mini fridge to a normal size fridge, more or less. Then there are micro satellites. Those are 10 to 100 kilograms, sort of luggage sized, anything from a briefcase to like a steamer trunk. Then there are nano satellites and pico satellites. Here you're talking more baked goods, things from the size of cookies to the size of big bread loaves. And then the smallest thing that we launch are called femto satellites. Those are anything less than 0.1 kilograms. The ones that have been launched into space right now are about the size of a credit card. And the ones that I personally work on kind of fall in this mid-range of microsatellites and nanosatellites. So bread loaves to suitcases, essentially. What I specifically do is make propulsion systems for them. Propulsion systems are just another way of saying a rocket that you stick on the back to move it around. And specifically, I tend to focus on propulsion systems for what are called CubeSats. CubeSats are just a subcategory of small satellites, but like the name implies, they come in cube forms. So every unit of them is called 1U. It's 10 by 10 by 10 centimeters, so about the size of a Rubik's Cube, and it's supposed to weigh about a kilogram. And we build up CubeSats from these single units, which are usually different types of subsystems. So say 2 units might be your propulsion system, and then another unit is your attitude, determination, and control system. Another unit is going to carry your payload, so maybe that's cameras to take pictures of the ground, or scientific instruments that need to conduct an experiment in a zero gravity situation. And so you build those together, kind of like building up Legos into a bigger block composed of those individual units, and that becomes your satellite. It's a way to make these satellites cheaper to produce, because you can have these single unit subsystems that are supposedly off the shelf. Realistically, people build them to order, but it's still a pre-existing design that can be rapidly produced, where traditional satellites, every single part of it is this kind of mod. So we work on these, a lot of small startups, like the company that I work at, also work on CubeSats. It's pretty, lots of bigger companies looking to build up these satellites, and you can just specialize in producing one type of subsystem in CubeSat form. So to start off with my first question for all of you guys, why do you think that we would want to put propulsion systems on small satellites and CubeSats? Got a couple options for you here. First one, to get them into space. Secondly, to move them around once they're in. All of the above. Lauren, do you want to launch the polls, or should I do that?
Yeah, I can. So I just want to say, if you don't see the poll that I'm about to launch, you can write the answer in the chat box. But if you see the poll, then just click on the poll what you think the answer is. Looks like about 30 people have responded to the poll. Let's see, it's still going up. 32 people, and some have written in the chat box, so you can see that, Maddie.
This is really fun. It reminds me of being in college with everyone's answers influencing each other.
Right, so you can see the answers, correct?
Yeah.
Okay, so I'll leave it up there while you talk about it.
Cool. Yeah, so the answer is actually, well, let me click onto the polls. It's B and C, which might be a little bit surprising to some of you, but we'll talk about why that is in a minute. The reason that A isn't correct, we don't use propulsion systems for CubeSats and SmallSats to get them into space, is that you can't build a big enough propulsion system for a CubeSat or a SmallSat to be efficient getting it into space. there's this thing called the rocket equation, which basically says that when you're trying to launch a rocket, most of the fuel is used to propel the previous kilogram of fuel that you used to propel the previous kilogram of fuel that you used to propel the previous kilogram of fuel that you used to propel the satellite into space. So it just becomes really inefficient to launch something very small into space. You're going to be using most of your fuel to send the rest of the fuel that is sending that rocket into space. So for CubeSats and SmallSats, propulsion systems, as I see them, really fix two big problems. The first problem is that space is really big, which might seem like an obvious thing to say, but it is very, very big. And so when we are sending these small satellites into space, there are kind of two routes that they take to get to space. And when they're headed there, they're going to one of three places, more or less. There's low Earth orbit, or LEO, which is anything under 2,000 kilometers above Earth. There's MEO, mid-Earth orbit, that's between 2,000 and about 36,000 kilometers. And then there's GEO, or geosynchronous orbit, at about 36,000 kilometers above Earth. GEO is special because at that orbit, you're moving at the same speed at which the Earth rotates. That means that if you have a satellite in geosynchronous orbit and you're standing on the ground directly beneath that satellite, no matter what time of day it is, if you look straight up in the sky, that same satellite is always going to be in the same place in the sky above you. So that's a really valuable orbit for a lot of applications.
Hey,
and when
Maddie,
we launch,
we have a question that might relate.
CubeSats and SmallSats into space.
Yeah.
What we do to get them into one of these three. Oh, totally, yeah.
So the question was, how are SmallSats launched into space?
We are getting right there. That is
great.
What I'm about to cover. So yeah, so to get the SmallSats into space, what we do is basically put them on a big rocket. We put a whole bunch of satellites on one big rocket, and we launch that big rocket into space. And then it basically goes to one of two places. It either goes to some orbit that might be GEO, it might be MEO, it might be LEO. And then once it gets there, it kind of chucks all of these little satellites out of that spacecraft. And then if you want to go anywhere other than where that single, what we call a rideshare rocket, dropped you off, you need your own special little propulsion system to go somewhere else. The alternate route is you can take a big rideshare rocket to the space station. And then at the International Space Station, essentially, the astronauts will, in a high-tech way, throw your SmallSat or CubeSat out of the space station and into low Earth orbit. And then if you want to go anywhere else, if you want to get away from those bunch of other satellites that got launched with you so that your signals aren't interfering with each other, you again need your own propulsion system to get where you want to go.
Hey Maddie, Lola was wondering where the planets.
Maybe get chucked out into LEO, but you're really interested in.
Lola was wondering where are the planets in relationship to the Earth orbits?
Oh, in the relationship to the Earth orbits. So all of the planets are way outside these Earth orbits. Geosynchronous orbit, compared to like where the moon is still super close to the Earth. These orbits, what we're talking about is thousands of kilometers away. The rest of the planets are millions and hundreds of millions of kilometers away. So it's kind of a totally different scale. There is actually one set of 2 CubeSats that have gone to Mars orbit. They used a really special propulsion system to get there. after being taken up on a big rocket headed for Mars. But those are the only ones who have gone into what we call deep space. Yet deep space is essentially anything beyond the moon.
We had two other questions that I think are related to this slide. Can rideshare rockets be reused?
So some rideshare rockets can be reused. If you've heard of SpaceX, which most people interested in space have at this point, they make reusable rockets, and their rockets are sometimes used for rideshare, but not all rockets can be reused when they're used for rideshares.
Nice. And Jacob has three questions. Can satellites orbit north-south over the poles? And what would happen if this was at the geo line? And his last question is, at what level is the space station at?
So the space station is in low Earth orbit, right at 2,000 kilometers, more or less. Geo is not over the north-south orbit. So geo is just, you have to be rotating in line with how the Earth is rotating. So if you were at that same height, but rotating over the north-south poles, you're not going to get that same effect where you stay in the same spot above the Earth at all times. But you can go in that polar orbit, is what it's called, I believe, if I remember back to the times when I learned those things. To get into a polar orbit, you either would need to take a rideshare that was bound for a polar orbit, or you would need to use your own special propulsion system to do what's called an orbital transfer. An orbital transfer is just any maneuver where you're firing your onboard rocket in order to be able to raise or lower or change the direction of your orbit. With reusable rockets, how do they stand re-entry? That's a really good question. It's a lot of careful engineering. It's a huge problem, really, that SpaceX has solved in some ways. It is dependent on a combination of all of the things that we use to re-enter atmospheres whenever we re-enter atmospheres. So that means heat shielding. It means entering at an angle where you're minimizing your friction against the atmosphere so that you're not heating up the spacecraft enough to burn it up. And then as you land, softening your landing either with some combination of a parachute and or rockets that are basically firing toward the ground as you fall toward the ground. So they're kind of propelling you up as you fall to soften the blow of landing. So yeah, you can, if you get checked out of the International Space Station into Leo and you have your own little rocket, you can then orbital transfer to another orbit. And that could be a polar orbit. It might be somewhere in MEO. If you have a really big propulsion system, maybe you can get yourself all the way to GEO. And then there's a second big problem, sort of the corollary to the first problem, which is that space is simultaneously really small, or at least the space around the Earth is quite limited and smaller than you might expect. So we launched our first artificial man-made satellite in 1957, Sputnik, and since then, this is what's happened. Right now, we have over 2,000 operational satellites in orbit, and these days we're launching more every other week. If you pay attention to space news, there is always a satellite launch going up. So this is not necessarily a problem, but it can sometimes become a problem. Right now, what you're going to see here is a super cool website that I highly recommend you check out. It's called Stuff in Space. The photo that you just saw, that's the operational satellites around us. This shows you all of the objects that are around us in real time that are bigger than about 10 centimeters. So those red things that you're seeing, those are operational satellites. But those blue dots are old, disused rockets. Basically, once you send most rockets up into space, they can't be reused. They just hang out there until they crash and burn again. And maybe the bigger problem is those little gray dots. That's just debris. It's junk. It's floating all around us, and there's more of it every day. And it not only just sits around up there, it can create its own junk, because stuff can happen like this. This happened January 29th, 2020 this year, when there were two satellites, IRAS and GGSE, headed toward each other on a collision path directly over the city of Pittsburgh. At the height of the fear about this, the data was saying that there was maybe a 1 in 20 chance that they would hit each other, which might not sound huge, but it's actually pretty massive in space probability terms. And estimates were saying they were probably going to pass within about 50 feet of each other, which is pretty scary. And these guys didn't happen to hit each other, but satellites do hit each other on a somewhat frequent basis. In the 90s, there was an incident where a bit of disused old French rocket actually hit another French satellite by accident. There was a time in, I believe, 2007 when an old Russian rocket satellite that was not in use any longer hit a functioning communications satellite, took down some communications. And then there are also intentional incidents. China in 2009, I believe, fired a missile to hit one of its own disused communications satellite, just to show that it could do anti-satellite missile firings. And when you get these collisions, something like this happens, where they break apart into tons of pieces, and that debris goes flying off, and that debris hits other pieces of debris, and that creates more debris, and those things go flying off. And this creates a chain reaction, which in a worst case scenario is something called the Kessler syndrome, where you basically get a cascade of collisions that, if it gets really bad, it could theoretically essentially surround us in just a cloud of debris that would hang out there for decades or centuries and make launches essentially impossible, because you just can't launch something and avoid getting hit by a piece of debris. And this problem is not in a worst case scenario right now, but it is pretty bad. We, like I said, we have about 2,000 functional satellites up there right now, but we have 34,000 pieces of satellite or full satellite that's just old and disused, doesn't work anymore, that's bigger than 10 centimeters across. The number of bits of debris that are smaller than that, between 1 and 10 centimeters across, is about 90,000. But the pieces that are less than a centimeter across, that's about 120 million pieces of debris. And this data is as of last November, so it's quite recent, and it gets worse. And it looks like we have a whole bunch of questions. Link to the website. Google Stuff in Space. It's www.stuffinspace.com. How far can a ship go? Need more context on that. Just a rocket ship in general? They can go pretty far. It depends on how many stages it has. Usually you take sort of 1 to 2 stages, which are sort of their own individual rockets, to get out of the atmosphere, and you shed those as they burn up their fuel, and then you have another stage to take you the rest of the way of where you need to go. But we've sent stuff out to the edges of the solar system, so really far. Is there a way to take the junk and old rockets out of space? That is a great question. There are ways that people are working on to do it. Some people are trying dragnets that clean up space. Some people are thinking maybe we can burn this stuff up with lasers. Some people want to send up fresh satellites that basically have little claws on them that grab junk and then intentionally dive into the atmosphere to burn themselves up. But really the best way to do this, and part of what I'm getting to here, is that you want to avoid creating junk in the first place, because you can do that with the big pieces, but the small pieces, which it turns out are really the problem, are just too small to track and collect. And so you can't really get those out once they're there. What you want to do is avoid this happening in the first place by either putting propulsion on your satellite so that at the end of its life, you can actively deorbit it, crash it back into the Earth, let it burn up in the atmosphere, and then it doesn't create space junk because everything is burned up. Or you can use that propulsion system while it's alive up in space to dodge pieces of debris that are headed at it. The problem with those two satellites, the GGSE and IRAS, that were headed toward each other this January, was that neither of them had propulsion, so they just couldn't get out of each other's way. All we could do from down here was watch and see if they hit each other. If an old satellite enters the Earth's atmosphere, would they burn up before they hit the ground? Most of the time. Not all the time. Sometimes bits get back down to Earth, but generally satellites are small enough that they completely burn up. What kind of satellites are SpaceX's Starlink satellites? I believe they are classified as traditional satellites. I think they're greater than 500 kilograms. They're definitely on the large end, and those are communication satellites. How do different units of satellites connect together? That really depends on the design. Honestly, screws, welding, it's not consistent. Yellow dots. I don't think there were any yellow dots. Or if there were, I don't know. How is that data collected? The data on space debris is collected by imaging, radar. Yeah, I don't know how else, but a bunch of different sources. That seems like something that is worth looking into. I'm going to take a break from answering questions here though, because those were super fun. But I do have some stuff to cover still. So yeah, like I was saying, the space junk that we really can't clean up is kind of the big problem, because we don't have any way to see it. It's just too small, and it still hits stuff with a huge amount of energy. So for instance here, if you have a 1 centimeter pane chip in orbit and it hits a satellite, what do you guys think the energy of that impact is most similar to in terms of something hitting a stationary object on Earth? Your options are an Indian pangolin rolled like a bowling ball, a kiwi bird thrown at the speed of a baseball, a Dawes porpoise on a luge, an elephant seal who can run as fast as Usain Bolt, or a base jumping water buffalo.
All right, so you should see the poll. And again, if you don't see it, just put your answer in the chat box. But if you do see the poll, make your selection. Oh, I gotta launch it. There we go. Now you should see it.
And I just hope you guys appreciate the examples because I spent a lot of time finding the right animals to fit my math.
I love the visuals that they create for me.
You want to be memorable, you know?
We have about not quite half. It seems like a lot of people are answering in the chat box. So I think at this point, the poll has stopped. Looks like you have a tie between the last two. I'm going to end that and you can go to your slide.
Okay.
Share results.
So to answer that, you kind of have to think about what we mean by impact energy. What we mean by impact energy is kinetic energy, which you can calculate as half of the mass of the object times its velocity squared. My keys are not working anymore. So what that means is that as something's mass increases, the kinetic energy that it carries increases linearly. It's a straight line relationship. But as its velocity increases, that has this relationship where it just shoots up hockey puck style. You guys have probably seen a bunch of graphs that look like this lately for world news reasons. But essentially, high velocity, almost regardless of the mass size, means that you carry huge kinetic energy. And for a centimeter paint chip in orbit, it has a mass of just 2 grams, but it's traveling at about 22,000 miles an hour, which means it impacts with about 90,000 joules of energy, which is coincidentally most similar to a doll's porpoise on a luge. But if you have something that is fairly small and moving fairly slowly, an Indian pangolin rolled like a bowling ball, you get fairly low kinetic energy, in this case 380 joules. But a comparably sort of small bird thrown significantly faster, huge increase in the kinetic energy. You're already at 3,000 joules, even though it's lighter. And for something large moving slowly, you still get a lot of, oomph out of that. And quickly, again, suddenly this huge jump up 1 million joules of kinetic energy. So those little tiny flecks flying around in orbit can still do a huge amount of destruction. So we use propulsion to try to avoid that. You can use it for orbital transfers, like we talked about in the beginning, once you get out of your rideshare, getting to where you want to go. You can use it for orbital maintenance, extending your lifetime, whatever it's using for. It can do for longer, but it's not the most useful thing in terms of either moving to somewhere new and exciting or avoiding the space debris problem. The space debris problem, you can avoid collisions by being able to move around in space. And maybe most importantly, you can actively deorbit at end of life. So instead of just hanging around in space for decades waiting to crash into something or for something to crash into you, you can deorbit, burn up in the atmosphere, and then you're no longer creating space. And that's what I do. I make these propulsion systems for small satellites. There are a whole bunch of different types of propulsion systems, and like everything in engineering, there are trade-offs between them. So there are things that have high thrust and low efficiency, like these chemical propulsion systems, liquid chemical, warm gas, cold gas, with low thrust but very high efficiency, like pulsed plasma thrusters, electrospray thrusters, and propulsion systems and electrical propulsion systems. That top half above that tilted line, that's your chemical. Below it is your electrical propulsion systems. And just thinking about these, what type of propulsion systems do you guys think are best suited to solve our two problems? So what's best suited to solve the space is big problem, getting around? What's best suited to solve the space is small problem, avoiding creating more debris up there? A, chemical propulsion, better suited to solve the space is big propulsion. Electrical propulsion, better suited to solve the space is small problem. B, other way around. Or C, both problems are too nuanced to make a blanket statement about propulsion suitability.
And I'm going to launch the poll right now. If you see it, take it. If not, put your answer in the chat box. And it looks like most people have responded in one spot or another, although got a few more coming in. So take about 10 more seconds, put your answer in.
Awesome.
All right. And share the results. It looks like A was your winner. Not by much though.
Right. So the correct answer is actually B, but I'm never going to, in a theoretical sort of way, take points away from people who say these problems are more nuanced than that. Obviously, everything has its own use in its own place. But generally, when you're trying to quickly avoid an oncoming hazard, you want chemical propulsion because you need to get out of the way quickly. Stuff is moving really fast up there. And electrical propulsion, because it's so low thrust, you just can't move quickly. Whereas if you want to move a large distance, solving that space is big problem, you don't necessarily care about how fast you're getting from point A to point B, but you do care that you are going to be able to get there without having to carry a huge propulsion system on your back. So something with really high efficiency is great for being able to move large distances like that. There are always different use cases here. You're always going to have to make a, measured evaluation of what your best option is. But personally, what I do is chemical propulsion systems. My company makes a warm gas system and a liquid chemical propulsion system. And I specifically do the design of those systems. So this, what you're seeing right here, this is what I spend most of my days doing. These, despite the fact that they're really pretty, are not photos of stuff. They're renderings of CAD, computer-aided design, that I spend most of my day just sitting at a computer, drawing things in 3 dimensions on my computer. And then I send those designs out to get builds, and our test and build engineers do all of the work to make my designs look way less pretty like this. And then after they build, the real thing, which is not as aesthetically pleasing, but does actually function, then we get to play around and test them a little bit. So what you're about to see here, the test firing of the main system that I work on. It's a bipropellant chemical propulsion system. Those are some of the best performing, highest thrust, most bang for your buck systems out there. So they're pretty fun, but it still kind of looks like a tea kettle when it fires. So this is what it looks like. As you can see, not the, and sometimes it gets a little more exciting. This is what you probably shouldn't do, but this is us having a big failure. You might have noticed my head creeping right into frame just before that explosion. Not a good idea. Don't do that. But as you can see, our successful fires are not that traumatic. Neither are failures, which is part of the benefit
Maddie,
of
can
working
you
in
try
such
to
a
show that
small
video?
format.
Can you try to show that
But
video
I want
one
to
more?
leave the rest of our time here up to an open Q&A.
Maddie, can you try to show that video one more time? Because I think it froze.
Totally. Here you go. Success that time?
Not really sure. There is a lag going on today with your, I don't know if it's on your end or everyone else's end. It seems like there's some lag going on today. I would say based on the time, if we can go into the Q&A,
Totally.
if all of you can, hopefully you'll stay with us for just a few more minutes while Maddie answers the questions, and then we'll wrap up for the day. We'd love for you to stay with us. So Q&A.
All right. Let's see. Would it be realistically possible to build something, another rocket, another space station, out of the space junk left in orbit? I love that question. I don't know. Yeah, that's a really cool idea. Sounds like a fun thing to propose to someone. Does shrapnel pose a risk to astronauts and manned rockets? Absolutely. If you've seen the movie Gravity, what happens in that is that Sandra Bullock is outside of, I think it's the space station, doing work on it. A piece of shrapnel hits it and her cord basically gets cut and she gets flung off into space. That's not as unlikely a scenario as you would expect given that it's in a movie. This is something that people are actually really worried about happening. What would be the consequences of the two satellites hitting each other over at Pittsburgh? They would have created probably thousands of new pieces of space junk that could have gone off and hit stuff. So that would not be great. What happens to the burnt up stuff? So it literally completely burns up into essentially ash, creates a bunch of more or less carbon that would be molecular in size. So it can't hurt anyone at that point. Kind of like a shooting star burns up. What is a luge? You should go to YouTube and look at videos of it. It's a really silly winter sport where people slide on sleds down ice tubes. What does the debris consist of? Tons of different stuff. Maybe most interestingly, astronaut poop. They chuck it out of the space station and it becomes debris up there, but mostly frozen bits of coolant and propellant coming off of spaceships, spaceship parts, so that's just metal and plastic rattling around up there. Anything that we send into space can become debris. If there's so much stuff up there and stuff is getting, is there enough mass out there that if you put it all in one big ball, you could get gravity? Well, everything that has mass has gravity. It's basically like everything except electrons. So anything has gravity. Now, if you mean the sort of gravity where we talk about when we talk about like a planet where it pulls itself into its own ball, probably not at the moment. Otherwise, we'd have a space junk moon out there. How many
Hey,
satellites have?
Maddie,
Yeah.
I'm going to interrupt for 1 second. Can you unshare your screen?
Oh, totally.
We're going to keep answering all your questions, but I know some people have to leave. So there's just one thing I want people to do before they leave us today. But we'll stay on and answer all your questions. It's just what I would love for you guys.
And I do also have, like we discussed, activity. Yeah.
All right, so we really need to get your feedback on today. So if you all could, hopefully you see this poll. Did it launch? Oh, my internet's on. It's going to launch in a second. Here we go. So if you could answer the first question on a scale of 1 being poor and 5 being excellent, please rate the overall virtual cafe today. And then the second part of that question is ranking 1 to 5, 1 meaning poor, 5 excellent. Rate the new knowledge you gained today. And then please put any comments you might have about what you learned or the cafe in the comments in the chat box. And once we're done this, we'll go back to the questions for anybody who wants and is able to stick around. So if you all can just, in the poll, if you see it, take the two poll questions. Otherwise, please write in the chat box rating the cafe and how much you learned, because this is very helpful to us as we offer more and more of these. So we really appreciate your feedback. And I'll leave it open just for about 15 more seconds, but you can keep writing in the chat box, and then we'll go back to the questions. All right, I'm going to end the poll. Thank you. I will stop sharing that. And then what I also just want to say as you guys leave us today, we are offering every Wednesday. Next week's topic is on the science behind maple sugaring. And I will tell you, you think you might know maple sugaring, but the science that our expert brings to this is really cool. So I encourage you to come and join us again. You do need to go and register. You'll see the lineup at that website, and I'll put it in the chat box as well. And sort of a teaser coming up at the end of the month, we actually have one on pandemics, understanding virology and immunology. So I'll leave this slide up, and Maddie, you can go back to the questions.
Cool, totally. And I do also, I prepared a post-cafe activity like we had talked about. If people are interested, I have those slides at the end of my presentation, but I can just send them to you, Lauren, or if people want to stay later, I can talk through with them. Up to you.
I can email something out to people.
Perfect. All right, questions. This is really fun. What 3D modeling software do I use? SolidWorks, but I've been trained on a bunch of them. That's just what our company has. It's a good one to know. A lot of design engineering companies use it. How many propulsion systems, how many satellites have propulsion systems designed by me? None at the moment. Our company is about to launch a satellite with the first one of our propulsion systems on it. Originally, one of my propulsion systems was supposed to be going up on another satellite later this year or early next year, but that mission got canceled. So now we're waiting for another chance to be able to launch it. Hopefully in the next year or so, it'll be in space. Currently, the one that I've spent most of my time designing is in testing stages. We're doing hot firings, basically. But yeah, it takes I've been working at this company for 1.5 years. It takes a while to bring a design from the idea all the way to flying on a satellite. If there's so much stuff up there and stuff is getting hit apart, why don't, I already did that one. Let's see. If all the fragments are magnetized, could you clean? Magnetic fields drop off quickly, so it would be hard. It's definitely a way that you could do it. What would be the price to clean everything bigger than 10 centimeters out of space? Probably billions of dollars. It's part of the reason that people just haven't done it. How do you choose what propulsion system to use? It's based on a lot of factors, how much it costs and what your budget is, what your exact mission parameters are. So are you doing something where you really care about being able to move quickly, like a formation flying mission, or is it something where you want to move slowly but over a long distance, like a deep space mission? A lot of consideration goes into that, depending on what your resources are and what you're trying to accomplish. What's the best type of propulsion to use overall? Same answer as the last question. It's always a trade-off between a lot of different factors, and it really depends on what you're trying to do. Why does the stuff burn up? The same way that your hands heat up when you rub them together because of the friction. As a satellite or a piece of space junk passes through the atmosphere, it's rubbing up against the atmosphere, and it just gets so hot that it spontaneously burns up. How much do rockets cost? That again really depends on what rocket you're buying. The systems that we sell, anywhere between $50,000 and $1 million, and that's considered really cheap. Why do you use satellites? What do they do? Also a great question. Most of what they do at the moment is take photos of the Earth in different spectrums. So you can take photos of the Earth in visual spectrum, infrared, whatever you want, but mostly people are using that photo data to do different things. You can do stuff like track climate and weather patterns. You can use it for spying on other countries. You can use it for evaluating things like how much farmland is being utilized and how it's being utilized. You can look at things like deforestation. But yeah, basically anything that you can imagine doing with a photo of the Earth, that's what people are doing with it at the moment. They're also used for communications. So making your cell phone work, doing things like satellite TV. Yeah, communications and imaging are pretty much all of it at the moment. I'm interested in learning SolidWorks. How did you learn? Got to go to college and get an engineering degree. The licenses are crazy expensive. Your college provides it to you. Your high school, depending on where you go, might. But what I can recommend doing is there is a free, most CAD software is more or less the same, just the buttons are in slightly different places. There's a free version that I believe Google produces. I can't remember the name of it right now, but I will give that to Lauren to give you guys in a follow-up email along with the project for this. What are satellites made out of? Mostly metal. It's a lot of metal, it's some plastic. Would I recommend SolidWorks for aviation design? Yeah, SolidWorks is a great design tool if you can get your hands on it, regardless of what you're designing. Unless you're designing like buildings, then you want something like AutoCAD. This might not be related and see light by them hitting our eye. What happens to all the photons that don't hit our eye? Can we not tell that they exist? Would light be a possible fuel source? Oh, that's an awesome question. Okay, I'm gonna start at the back end of it. Would light be a possible fuel source? You can use light to convert into, so for propulsion, you need to be able to throw something with mass out of the back of your spaceship in order to make it go forward. Every action has an equal and opposite reaction. So if you want to move in one direction, you got to throw something to move in the other direction, essentially. Light doesn't have any mass, so you can't use it as the thing that you throw out the back. But you can use light, like you can use a solar panel to turn light into electricity, and then you can use that electricity as the thing that like throws stuff out the back. So you can use it to like energize other particles that you then throw out the back. So sort of in that way. But the other way you can use it is, even though light doesn't have mass, it does have momentum, which is something that I as an engineer don't really understand. You would need a physicist to explain that to you. But basically sails, which is what it sounds like. It's a big sail that when light hits it, it imparts momentum onto that sail, and that can propel a spacecraft. It's mostly used for stuff that doesn't need a lot of specific pointing, like deorbiting. But so in that sense, yeah, you can also use it as a means of propulsion. Photons that don't hit our eye, we can tell that they exist using other sensors that can detect photons. But yeah, I guess if it doesn't hit your eye, you can't see it. We can tell that they exist through a bunch of different measures. What they do when they hit your eye is they cause a change in a particular protein. No, that might not be right. I'm gonna have to go back to my neuroscience textbooks on that one. I forgot most of the neuroscience stuff by this point. But light can cause physical changes to things, and we can detect those physical changes. What's the difference between Blender and SolidWorks? Which is better? I've never used Blender. I don't know. What's the Hall method? Okay, so the Hall effect is something that I really don't understand, and I would love someone to explain to me. It's a method of using like electricity and magnetism to charge particles to throw them out of the back of your spaceship to propel you forward. It's very confusing to me. I'm a mechanical engineer. I really don't understand electrical propulsion systems on anything more than a very surface level. If you had a ship going through re-entry, it would heat up. Could you use that heat energy as a power source for something? Electricity, part of another launch. Could this be used if you just scratch the atmosphere of Earth or another world as a rechargeable fuel source on a satellite or interstellar ship? Sort of. Okay, so as you go through re-entry, it would heat up. You could theoretically use that heat as an energy source for powering something. But because that heat is created by friction, which is essentially dragging back on your ship, your ship is falling further out of orbit as it happens. So it's not really rechargeable unless you have more fuel on board to boost your orbit back up again. So you wouldn't be able to use it for like orbital maintenance. If you could figure out a way to do that, you'd have figured out how to create a perpetual motion machine, and you can't create a perpetual motion machine. Or if you can, like, you've broken all of our physics. So in that sense, no. Lauren, I have time here, but I don't want to make everyone else stay. Do you want me to stop answering questions?
Well, I would say scroll through. I think some of these questions have already been answered. Maybe time for one or two more. And then if you are okay when you send out the packet, if you're okay with giving out your email, maybe you can be a resource for people. who
For
might
sure.
have additional questions.
Yeah, and I have a feeling people might also have questions about that additional project if they want to do it. So I'm also absolutely available for.
So how about just one or two more out of the chat box, and then I do think we need to sign off for today.
Let's see. Sure thing. How do you make super tiny satellites? That's a fun one. It's really difficult because most parts that are out there are not supposed to be made super small. So we have to design most stuff more or less from scratch in order to miniaturize those big satellites. And some of the physics that you use to make big satellites work, like some of the propellants that we use to fire big rockets, just don't work when you shrink them down. So we have to come up with totally new ways of doing that. For instance, the fuel that most big rockets use is called hydrazine. If you've watched The Martian, that's the fuel that he's trying to convert into water and oxygen when he blows himself up. We can't use that for small satellites. It doesn't work well when you try to do it small for a whole bunch of physics reasons. So we make our rockets out of, what I mainly focus on is hydrogen peroxide, like the stuff that you have under your sink, except the stuff that you have under your sink is 3% hydrogen peroxide, and the stuff that we use to make our rockets is 90 to 98% hydrogen peroxide. So it's just way more explosive and energetic. But yeah, making satellites tiny is actually really difficult. Right, maybe just one more. Oh, can particles in space damage computer systems by flipping bits? Not the particles that we refer to as space junk, but particles like electrons, photons, I don't know if photons will do it, but yeah, charged particles. The sun throws off a bunch of what are basically just charged protons. Those can wreak all sorts of havoc on computers. So yeah, absolutely, it's a problem. It's a reason that we do what's called radiation shielding on pretty much everything that goes past low Earth orbit. In low Earth orbit, there's this thing called the magnetosphere around the Earth, which is what creates the northern lights. It's basically a big shield of orbiting charged particles that create this essentially magnetic shield around the Earth, and they deflect incoming particles, and that's what protects all of us from not getting crazy amounts of cancer from all of the particles flying around in space. It's also what protects computer systems on board satellites in low Earth orbit from getting all jammed up with tons of different particles flipping bits all over the place. But once you get outside of that, yeah, you're totally open to the radiation of space, and it'll mess you up in all kinds of bad ways.
Well, this was fantastic. You know, that I've been counting, I can see it. We've had 50 questions today. That is phenomenal. I can't get over how just incredible the questions were that everyone asked you. And Maddie, thank you so much for taking the time. What a wonderful and informative cafe. Those that are still with us, we'll send out some information as well as a contact if you find that you still have some questions for Maddie. She's a great resource for you. And we hope that you come back for more cafes, because we've got lots of interesting people coming up that can share some really cool science with all of you. So I see you all saying thank you, and we're going to say thanks back to you. If you put your mouse down at the bottom of the screen, all you have to do is choose leave the meeting. to leave, but thank you so much for joining us today. Stop.